Education and clinical diagnostics are rushing to integrate generative AI. Psychologists are feeding complex student evaluation data into large language models to draft individualized education programs and clinical reports. Look at this split screen. On the left, a traditional evaluation report documents a WISC-5 full-scale IQ score of 78. On the right, an unconstrained AI model ingests that data and generates a definitive summary. Students scored a 78, placing them in the intellectually disabled range. That conclusion is psychometrically false. A score of 78 is a point estimate, bounded by the standard error of measurement. The true score exists within a confidence interval spanning 73 to 83. The AI conflated a statistical association with clinical validity. Large language models operate on text prediction. They are trained to pattern-match linguistic tokens, not to calculate statistical variance. When these models encounter a point estimate, they strip away the required mathematical uncertainty. They produce authoritative, fluent prose that sounds clinically accurate, but lacks the structural boundaries of actual psychometrics. We have created a compounded error. We are using hallucination-prone statistical engines to interpret static 20th century cognitive measurements. To solve this, we have to look specifically at the mathematical failures of unconstrained AI, map the exact structural engineering required to bound those systems, and finally, replace the outdated cognitive tests themselves with a new model of intelligence. Treating a language model's linguistic fluency as proof of clinical validity produces systemic, legally invalid educational documentation at scale. The AI failure begins at the very base of classical test theory. This is the standard classical test theory formula. Every obtained score is an estimate, modified by the standard error of measurement, which relies on the test's standard deviation and reliability coefficient. An AI system cannot hold this mathematical relationship in memory. It collapses the formula into a single, rigid coordinate, ignoring the measurement error entirely. The problem multiplies when we move from classical summation to modern, large-scale educational assessments built on item response theory. This U-shaped curve represents a test information function in item response theory. The conditional standard error is not constant. The test is highly precise in the middle of the curve, but that precision degrades rapidly at the extreme high and low ends of student ability. Language models ignore this curve. They apply the exact same interpretive language and goal calibration logic regardless of where a score falls on the function, generating baseline metrics that exceed the instrument's actual precision. Stripping away conditional measurement error converts standard diagnostic uncertainty into a dangerous false precision. The mathematical errors extend into construct interpretation, specifically within Cattell-Horn-Carroll, or CHC, theory. CHC theory organizes cognitive abilities into distinct categories. Fluid reasoning and crystallized intelligence have different factor loadings, distinct neurological substrates, and separate developmental trajectories. They are not interchangeable. A language model groups information by semantic proximity. It will match vernacular terms, eagerly conflating a working memory index with a processing speed index because the words appear together in its training data. Here, we see two distinct data clusters representing separate test batteries. An unconstrained AI will synthesize these results into a single profile, ignoring that they possess independent normative samples and overlapping variants. To prevent this, psychometricians rely on Flanagan's cross-battery assessment methodology. This methodology dictates strict rules. It acts as a structural gate, explicitly prohibiting the combination of co-normed batteries to preserve interpretive independence. Without these methodological constraints hard-coded into the system, an AI will fabricate clinical connections between mathematically incompatible datasets. Fixing these errors requires abandoning prompt engineering entirely in favor of strict system architecture. You cannot instruct a language model to not hallucinate when processing clinical data. The statistical weight of its training data will always override safety prompts. The only legally sound solution is an anti-fabrication architecture, a system where the AI operates within rigid, predefined data constraints. Unstructured text locks into a rigid data schema. Standard scores and confidence intervals map to isolated, mandatory fields. Next is domain isolation. AI agents are blocked from crossing data silos. A reading agent cannot access behavioral data without an explicit relationship. Third is the source traceability requirement. If a schema field for a confidence interval is empty, the system structurally blocks the AI from generating any output for that metric. Finally, human clinical opinions, diagnostic impressions, and eligibility conclusions are stored in read-only schema sections. The AI generation agents can read them, but they cannot moderate, alter, or contradict the psychologist's exact findings. A defensible platform does not rely on the intelligence of a large language model. It relies on data architecture that makes psychometric fabrication mathematically impossible. Bounding in AI solves the clinical compliance problem, but it exposes a deeper flaw in the underlying cognitive tests themselves. Traditional tools evaluate static memory, vocabulary, and unassisted processing speed in artificial isolation. They measure what a student already knows in a closed environment. But look at this kinetic mechanism. Modern human environments are highly interconnected, dynamic, and data-rich. Problem solving happens in motion. Human reasoning is no longer limited to internal processing. It is continuously extended by machine learning, digital tools, and collaborative external systems. Measuring isolated recall in a vacuum fails to capture a person's actual capacity to adapt, iterate, and solve novel problems in real-world contexts. To measure how humans actually think today, we must transition to the Hewlett Dynamic Iterative Analytical Reasoning Model, or HD-AIR. HD-AIR evaluates intelligence as a profile of reasoning behaviors. It captures how a person updates their mental models when given new tools and increasing complexity. This shift from static snapshots to dynamic tracking leads to a new theoretical geometry, recursive spiral intelligence. Traditional IQ tests attempt to locate a student's fixed position on a bell curve. HD-AIR, however, tracks the rate of cognitive movement. This requires a spiral geometry. Each cognitive cycle builds upon the validated knowledge of previous iterations, while simultaneously expanding into unexplored conceptual territories. The model formally incorporates tool use through AI-augmented problem-solving. When external tools attach to human reasoning, the spiral's radius widens, and the trajectory accelerates. True evaluation must measure the trajectory and rate of a learner's cognitive acceleration, moving far beyond static snapshots of retained facts. Modernizing our approach to cognitive measurement requires two simultaneous structural shifts. First, we must abandon unconstrained language models and build rigid, architecturally bounded platforms to evaluate clinical data safely. Second, we must abandon static 20th century testing and adopt dynamic, performance-based frameworks like HD-AIR. AI is a tool to accelerate human cognition and track its growth. It should not be used to fabricate narratives for outdated tests. To successfully partner with artificial minds, we must measure intelligence as a trajectory of perpetual growth.